Freezing point depression and boiling point elevation are probably the two best known of the colligative properties, but there are others, and one that I want to talk about here is maybe even a more fundamental property called vapor pressure lowering. And so what I'd like to do, though, is show you that, in fact, vapor pressure lowering has a tangible effect that actually helps us understand why freezing point depression and boiling point elevation occur. So I want to suppose, for example, that we have a solution that is approximately ideal. Okay, so in other words, we can write the total pressure, the total vapor pressure of the solution as simply equal to contributions from its solvent and its solute. Okay, but it's not exactly ideal because the solute in this case we want to specify is non-volatile. That is to say, it's not readily escaping into the vapor phase, and yet it still is occupying some of the mole fraction. So in effect, the total vapor pressure is going to be x1 times p1 star, but x1 is less than or equal to 1, so that means that this is by necessity going to be less than the actual total vapor pressure of the pure substance. All right, so how can we understand this in a very physical way? All right, so what we're predicting is that the vapor pressure of the solution is going to be less than that of the solvent by itself. All right, and that certainly vapor pressure lowering certainly already suggests that to us. Okay, so if I were to consider a beaker full of some solution, and I'll make my dilute solute be these dark particles that I'm drawing in here. All right, so there's a few of them, occasionally one's on the surface, but they're distributed throughout the solution like this. And now I want to surround these dilute solute particles with solvent particles, which are going to be now these open red circles. Okay, now you'll notice I'm purposely drawing little solvation shells around each of the solute particles, because in essence that's what happens in these solutions, is that yes, we do have a lot of free solvent out there and forming little clusters of solvent molecules, but we also have cases where these solvation shells are occurring that occupy solvent molecules. And in particular, when we have a non-volatile solute, one of the reasons that it's non-volatile is that it sticks well, it's a technical term, sticks well to solvent molecules. All right, so it's not going to vaporize quite so readily, but when it sticks well to solvent molecules, it's also holding some of those solvent molecules back from evaporating themselves. In addition, it occupies some sites on the surface. All right, so it's preventing some of these solvent molecules from evaporating into the vapor phase, because those sites on the surface are being occupied by solute molecules. All right, so the net result is it's going to reduce the tendency for vaporization. All right, but why would this be connected necessarily with freezing point depression and boiling point elevation? Well, let me show you why this would be the case by drawing a phase diagram. So I'm going to draw a phase diagram over here, and initially what I'm going to draw in this phase diagram is a phase diagram of the pure solvent. So remember, phase diagram was a graph of pressure versus temperature, and the typical shape for these phase diagrams, they come up to a triple point, then they go on up to a critical point, and then there is a solid liquid coexistence curve that separates the solid and liquid. So I've got solid here, I've got liquid here, I have vapor down here. This is the critical point. All right, and these coexistence curves, especially the one here that separates solid and vapor, and the one here that separates liquid and vapor are the vaporization curves. I'm going to focus on the liquid vapor curve because the solid vapor one is not affected as much. But now I want to show you what happens when we have a solute present. So the solute is going to reduce vaporization, as we've mentioned. And so what it does is it's moving this curve downward. Okay, it's not a large move downward, but all the points along this curve are going to move slightly downward. So if I were to redraw it now for the solution, it would come up like this. All right, so that's the effect of the vapor pressure lowering. But now it will also shift over the position of this triple point, which also shifts over, interestingly, the solid-liquid coexistence curves as well. So in effect, what we have, if I were to look now at the pressure of 1 atmosphere, which is where we have normal melting and normal boiling point, so this is 1 atmosphere, and just draw this across, what I'm going to have is the following. This is the normal boiling point, so this is T-vape, and this is the boiling point of the vapor, of the solution rather. So what I have here is this is the change in that boiling point, and you'll notice that it is elevated. So this is elevated above the pure boiling point, which is over here. So in fact, the fact that vapor pressure was lowered actually accounts for that. We can also think of this in terms of the fact that when you lower the vapor pressure, you have to raise the substance to a higher temperature in order to get it to achieve a vapor pressure of 1 atmosphere, which would represent its normal boiling point. Now on the other end, over here, we have a shift that has gone downward. Okay, the fact that the vapor pressure was lowered shifted the triple point over, shifted this solid-liquid coexistence curve over, and so the delta T fusion over here has lowered, so we have lowered the freezing point. All right, so this diagram, I think, helps to illustrate why these things are connected to one another. It also demonstrates, too, that the freezing point depression and boiling point elevation are really just different manifestations of, in effect, the same phenomenon.